Hello everyone. Today we're going to focus on questions that require us to use the first fundamental theorem, but it's going to look very different. So these are problems where we have to use the theorem, but we're also going to be given an initial condition that we have to work within. So let's get started and take a look at how these are going to go. All right, so this formula obviously should look familiar to you. We called it the fundamental theorem, the first fundamental theorem of calculus. And we defined a couple different things. We definitely defined these as our bounds, our A and our B. And if you think about it, when you're thinking about the area under the curve, A is your starting value, it's your first place, and B is your ending value. And the problems that we're going to see today, we're going to be talking about an initial value, and we're going to be solving for a final value. So I want you to think of A, okay, as the beginning and B as the end. So if I wanted to solve for f of B, which would indicate our ending, okay, f at the place where B is, then the first thing I would do here, just algebraically, to get f of B by itself, is I would add f of A to both sides. And so what you'd have then is f of B is equal to f of A plus the integral from A to B of f prime of x dx. And this is the formula we're going to be working with a lot. All right, this I want you to think of as what we want, what we're looking for. This is our beginning or our initial, and this is our change. So that's how much has changed in the time allotted. And so if we start with our initial and we add on the change, we'll get our ending or what we want. Okay, so if we take a look at this first example, it says if f prime of x equals 4x cubed minus 3 and f of 2 is 7, then what is f of 5? All right, so what I want you to understand is that in these parentheses, obviously we're given f prime, and then we're given a value of f of 2, and we're looking for f of 5. In the parentheses there, those represent your A and your B. Okay, so if we took our first fundamental theorem, and we want to plug in the values kind of that we know here, we would say the integral from 2 to 5, there's our A and our B, of f prime of x dx is equal to f of B, but we just said our B is 5, so I'm going to say f of 5 minus f of A, which would be f of 2. Okay, now we just said that it's f of 5 that we are solving for. That's what the question is asking for. So if I just used kind of the maneuvering that we just did on the previous one with the general formula, to get f of 5 by itself, I'd add f of 2 to both sides. So I'd say f of 5, what I want, is equal to f of 2 plus the integral from 2 to 5 of, and I'm going to go ahead and plug in 4x cubed minus 3 dx. And so we should be able to evaluate this using what we know. So we can say f of 5, what we want, is equal to f of 2 is 7 plus the integral from 2 to 5 of 4x cubed minus 3 dx. Well, I'm going to go ahead and take the integral of 4x cubed minus 3. So I'd hold the 4, and this would be x to the 4th over 4 minus 3x. And I want this over the bounds 2 to 5. And so 7 plus, this obviously is just going to be x to the 4th, which is going to be 5 to the 4th minus 3 times 5 minus 2 to the 4th minus 3 times 2. Okay, so let's see if we can figure this out. We'd have 7 plus, let's see here, I know that we have 5 to the 4th would be 625 minus 15 would be 610 minus 2 to the 4th is 16 minus 6 is 10. Okay, so that would be the same as 7 plus 600, and so we end up with f of 5 equaling to 607. All right, so I just want to kind of summarize things for a second and make sure that we are all on the same page because we're not going to have to rearrange the way we did here every single time. All right, I really want to kind of get this in your head, the way that we want to look at this. So we're going to kind of think of this. All right, I really want you to understand this, that we're looking at f of b equals f of a plus the integral from a to b of f prime of x dx. That this is what we want. And I know we said this earlier, but I really want to star this. This is important. This is our initial condition. And this is the change. And so we want to make sure that this is the formula we're going to use as we move forward. And especially as we get into more wordier problems, it's going to be helpful to think of it in this term. Okay, let's take a look at this next problem. It says a particle moves along the y-axis with velocity given by v of t equals 3t squared plus 8t for time t is greater than 0. If the particle is at position y equals 5 at time t equals 2, what is the position of the particle at time t equals 4? All right, so they are giving us velocity. As I unpack this question, I want to just kind of pick it apart. So they are giving us velocity, but look, they're looking for position. Okay, so this is kind of backwards from what we have been used to doing. They usually give us position, and they want us to evaluate velocity or acceleration. Well, now that we know integration, right, we are going to go backwards from velocity to get position, which means we're going to do the integral of velocity to get position. All right, so now let's look at the question a little bit closer. It says if the particle is at a position y equals 5 at time t equals 2. That right there is an initial condition. And they want the position of the particle at time t equals 4. Okay, so let's kind of write down what we have. All right, what do we have? What's our initial condition? Well, that would be y of 2 equals 5. And I used y because it says it's moving along the y-axis. And so my position was y equals 5 at a time t equals 2. So y of 2 equals 5. And I want y of 4. So that's unknown to me. All right. And so if you remember the formula we said we write down what do we want. So y of 4 is what we want is equal to our initial condition, which would be y of 2, plus the integral, the change. And that would be from 2 to 4. So in between the start and the end of what? Well, if we took like we just said, we take the integral of velocity, we'll get position. So integral of v of t dt. Okay, so let's go ahead and plug in what we know. We say y of 4 is equal to, y of 2 is 5 plus the integral from 2 to 4 of v of t is 3t squared plus 8t dt. All right, so we have 5 plus, let's see here, the integral of 3t squared plus 8t would be 3t cubed over 3 plus 8t squared over 2. And then that we are evaluating from 2 to 4. Oops. All right, so 5 plus. Now we're going to go ahead, obviously the 3's cancel here, so it would just be 4 cubed plus, this is going to be 4t squared, so 4 times 4 squared, or 4 times 16. Okay, that was the upper bound, minus, let's plug in our lower bound, that would be 2 cubed, which of course is 8, plus 4 times 2 squared is 4. All right, so 5 plus, let's see here, this is going to be 64 plus 4 times 16 is another 64. So we got 128 minus 8 plus 16 is going to be 24. So minus 24. Okay, finishing this off then, we would say y of 4 is equal to 5 plus, it looks like 104. So 109 is our position at a time of 4. Okay, this next one says a particle moves along the x-axis so that at any time t is greater than 0, its acceleration is given by a of t equals sine pi t over 4. If the velocity of the particle is 6 at time t equals 0, then what is the velocity of the particle at times t equals 3. So this is very similar to the last question. This time they are giving us a function for acceleration, okay? And they're giving us an initial condition with velocity, and they're asking us for velocity. So here is our initial condition, okay? That the velocity at time 0 is 6. And they're asking for the velocity at time 3 and saying, what is that? Okay, what I'd like you to do is go ahead and pause the video. I want you to write out the formula of exactly how you would set this up. Remember, it's what we want is equal to the initial condition plus the change. So first of all, write out the formula, then go ahead and plug in what you got, and then come back to me and make sure that we agree. Okay, so take a look at what I have here and let's compare it with yours. So we said v of 3 is what we want. It's equal to the initial condition, v of 0, plus the integral. This is the change, and it's from beginning to end, so from 0 to 3 of the acceleration dt, because I know if I go backwards from acceleration, I will have velocity. So I go ahead and plugged in my v of 0 is 6. And then plugged in my acceleration function is sine pi t over 4 dt. All right, so now I'm ready to evaluate this. Hopefully as you're looking at that and thinking about taking the integral of the sine pi t over 4, you're realizing that what's inside the parentheses, what the angle is more than just t, more than just a single variable. And so hopefully you're thinking, oh yes, I need to do u substitution. So over on the side here, I'm going to go ahead and say that u is equal to pi t over 4, and so so du is equal to pi over 4 dt, and so 4 over pi du is equal to dt, so I just multiply by the reciprocal there. All right, so then I'm ready to go ahead and rewrite this over here. So I'm going to say v of 3 is equal to 6 plus the integral. I'm going to hold on to my bounds for a second, and it would be the sine of u times 4 over pi du, because of course I'm replacing the 4 over pi du in for dt. All right, so now I'm going to fix my bounds. So my upper bound, I got to plug in a 3 into this. So u is going to equal, let's see here, it'd be 3 pi over 4. Okay, so there's no real calculating, that's just what it is, 3 pi over 4. And the lower bound there is going to be 0 pi over 4, which of course is just 0. Okay, so now that we have that, we're ready to go ahead and take the integral. Now this 4 over pi here is just a constant, so I'm going to kick it out to the front. All right, so I have v of 3 equals 6 plus 4 over pi times, all right, now the integral of sine u is negative cosine u, and then we're going to evaluate that from 0 to 3 pi over 4. All right, so let's keep chugging along here. V of 3 is equal to 6 plus 4 over pi times, it's going to be negative cosine of 3 pi over 4 minus negative cosine of 0. All right, so let's see here. 6 plus 4 over pi times cosine of 3 pi over 4. Well, I know pi over 4, the cos of pi over 4 is root 2 over 2. 3 pi over 4 would be in the second quadrant where cosine is negative. So it's negative root 2 over 2, but then it's negative of that. So I'm going to say positive root 2 over 2 minus cosine of 0 is, of course, 1, but it's negative of that. So minus negative 1 would be plus 1. Okay, so this is getting kind of yucky here, but I'm going to go ahead and distribute this 4 over pi through. So I'm going to have 6 plus, all right, when I multiply 4 over pi times root 2 over 2, the 2's will cancel into, the 2 here will cancel into the 4, and it would be 2 root 2 over pi. Oops. plus, obviously, 4 over pi. And so last thing I could do is just change this 6 to 6 pi over pi, so they all have a common denominator. And so I would end up with 6 pi plus 2 root 2 plus 4 all over pi. And that is what v of 3 is equal to. Okay, so as we move forward in these problems, you can see it's really important that we know how to set it up, but then obviously all of those other skills of integration and u substitution, all of that comes into play because we have to be able to correctly execute all of that math in order to get to our final answer. All right, let's try another one. Okay, if we read through the next one, it says a pizza heated to a temperature of 400 degrees Fahrenheit is taken out of an oven and placed in a 75-degree room at time t equals 0 minutes. The temperature of the pizza is changing at a rate of -3 root t degrees Fahrenheit per minute. To the nearest degree, what is the temperature of the pizza at time t equals 4? Okay, as I unpack this question, how do I know I'm talking about integration here? Well, because I'm going from a rate of temperature change to the actual temperature. That's going backwards. Remember, rates are the same as slope. That's derivative. So you're not going from temperature to rate of change. You're going from the rate of change backwards to finding the temperature. You're looking for what the actual temperature is. And so that is going backwards. That's integration. All right, so if you look through, we got to unpack what do we need. Well, I know that I want to find the temperature at 4 minutes. That's what I want. I also can tell that my initial condition, the temperature at 0, the temperature of the pizza at 0 is 400 degrees. Okay, so that's important that it's the temperature of the pizza, not the room. All right, so and I can tell also that I have this rate here, and that's when I'm going to go ahead and integrate. So that's going to find out my what's changing, how much has changed. So I would say what I want is t of 4, and that's equal to the initial condition, t of 0, plus the integral from times 0 to 4 of the rate -3 root t dt. All right, so t of 4 is going to equal, t of 0 is of course 400. I'm just going to take out this constant -3 and put it in front, so it'd be -3 times the integral from 0 to 4 of, and I'm going to rewrite this as t to the 1/2 dt. All right, so let's go ahead and do that integral. So t of 4 is equal to 400 minus 3 times, all right, I would say t to the 3/2 times 2/3, and that would be, of course, from 0 to 4. All right, this 2/3 and this 3, I can go ahead and cancel those 3's, so it just ends up, and that 2 can come out front, so I have 400 minus 2 times, let's go ahead and plug in the 4 and the 0, the upper and lower bound, so 4 to the 3/2. Remember, we always do the root first. So the square root of 4 is going to be 2. 2 cubed is going to be 8 minus, obviously 0 to the 3/2 is just 0. Oops. And so I have 400 minus, this is just going to be 16. 400 minus 16, so it only dropped, the change was only 16 degrees here. So I would say my temperature after 4 minutes is going to be 384 degrees. Okay, for the next few questions, we're going to shift a little bit to a geometric approach. And these are also very popular on the AP exam. And so you're given here, it says the graph of f prime, which is, of course, the derivative of f, is shown in the figure above. Then they give you this initial condition. And notice that this is the graph of f prime, but they're giving you a condition about the original function f. And then they say to find the following. So in the first one, it says, go ahead and find f of 5. So remember, if you want something, this is what I want, then it's equal to my initial condition, which I can tell here is f of 1, plus the integral, okay, what changed between my lower and upper bound, between what I start with and where I end. So between 1 and 5 of f prime of x dx. Okay, so this is what I have to evaluate. And if I'm evaluating it from a graph, then I have to use my area under the curve geometric approach. So I'm looking specifically at the region between 1 and 5. And this is the area under the curve that I'm concerned about. Okay, so this is a nifty one. It's a little bit different than we've had in the past, okay? So how am I going to find that area under the curve? Well, I clearly see that I have this semicircle kind of cut out here, but it's floating up in the air. If I kind of envision taking and closing off between 1 and 5 at a height of 3, I can see this whole piece as a rectangle, but I have to cut out this semicircle, and then what's left over is the area under the curve. Okay, so that's kind of what I'm going to do for this change right here. All right, so let's start off with f of 1. I know I was given as 5. Now plus. All right, so now I have to do the area under the curve piece. So I'm going to start off with the area of the rectangle here, which would be, let's see here, base is 1, 2, 3, 4, and my height is 3. So I'm going to say 4 times 3 minus the area of the semicircle, because we have to cut out that. It's kind of one of those shaded region problems back from geometry. So the semicircle here has a radius of 2. So of course semicircle formula is 1/2 pi times the radius squared, so times 2 squared. So I would have 5 plus 12 minus 2 squared is 4, half of that is 2, so minus 2 pi. So my answer here would be 17 minus 2 pi. Okay, the next one we're going to look at here is f of 0. And so again, this is what I want, but I have this initial condition. So f of 0 is equal to my initial condition, f of 1, plus the integral from, now I have to be careful of my bounds here. Remember that when we do this, okay, that my initial condition is where we're starting, and what we want is where we're ending. So we're going to go here from 1 to 0, and I know this feels a little backwards, and in fact it is, and we're going to fix that in a second, but you have to be careful to go from the initial value to your ending value. What you want is where you're ending, and so that has to be the upper bound, and your initial has to be your starting, that's your lower bound. All right, of f prime of x dx. All right, so because of that, because the bounds are backwards from what we like, okay, the bigger ones on the bottom, we're going to go ahead and rewrite this. F of 1, of course, is 5. And then we have minus the integral from 0 to 1 of f prime of x dx. All right, so remember when we switch those bounds around, we have to negate our integral. So we have 5 minus, all right, so we're looking from 0 to 1 here. Okay, so from 0 to 1 is definitely a triangle, and so that would be base times height divided by 2, or half base height. Our base of this triangle, it looks like, is 1, and our height is 3. So we're going to go 1/2 times 1, times 3. And so that we would have, I'm going to change this to 10 halves minus 3 halves. So 7 halves is the answer for that one. Okay, so we're going to try 2 more of these. Again, we are using the same graph, the graph of f prime, and we have the same exact initial condition. So we're working with the same information, just 2 more practice problems. So the first one here is f of 11. So f of 11 is what we want. That's where we're ending. So we start, it's equal to the initial condition, f of 1, plus the integral from our beginning, which is 1, to our end, which is 11, of f prime of x dx. Okay, so we're going all the way from 1 to 11. Okay, so we have all of this, and that we already found from 1 to 5, so we'll grab that from the other problem. And then we're going to add on this, and then we have this down here as well. Okay, so let's kind of pick this apart. Okay, so the area from 1 to 5 under the curve, we remember we found that earlier to be 12 minus 2 pi. So since we already found that, we're going to hold on to that. All right, I'm just going to kind of stick the areas right in here, and then that might help us simplify. So this is a triangle, obviously, from 5 to 7, and my base is 2, and my height is 3. So that would be 1/2 times 2 times 3, which is 6, half of 6 is 3. All right, so that's going to be this. And then down here, I clearly have a trapezoid from 7 to 12. So my bases, remember, are the parallel sides. And it looks like this base is a length of 1, and this is 1, 2, 3, 4. So I would have 1/2. My height here is 2. And then my bases are, like I said, 1 plus 4, or 5. So I'm going to go ahead and call that an area of 5, which of course it's below the x-axis, so that was going to be a -5. All right, so now that I kind of have all those pieces, I should be able to answer this question really quickly. So f of 1 I know is 5, and then plus the integral from 1 to 11, well, we're just going to add up all these pieces. So we were going to say the 12 minus 2 pi plus the triangle, which was 3, minus, because it dipped below the x-axis, the trapezoid of 5. So we're just going to kind of, now 5 and 5 would go away, and so we end up with 15 minus 2 pi as the answer for f of 11. Okay, the last one we're going to try here is f of -4. Okay, so again, start by writing out your formula. F of -4 is what you want. It's equal to your initial condition, f of 1, plus the integral from, remember, you start at the bottom 1 and you go up to -4. And don't worry about the fact that those are backwards. We'll flip them around in a second. F prime of x dx. Okay, so yes, those are backwards, so we're going to go ahead and rewrite this. F of 1 we know is 5 plus, oops, I'm going to go ahead and say that that's minus. So minus the integral from -4 to 1 of f prime of x dx. Okay, so we want to go from -4 to +1. So basically the other part of this graph here. So we need this here and this here. This one we already found earlier to be 3/2. Okay, that was 1/2 base times height. And then this one here, well, let's see, it's a triangle. I have a base of 1, 2, 3, 4, and a height of 2. So I'd have 1/2 times 4 times 2, which of course is 4. So we're going to say that this has an area of -4. So if I have those pieces now, I can go ahead and plug in and get my answer here. I'm going to go ahead and say that this would be 5 minus. Okay, now I'm just going to collect up all those areas that I have in green there, and I'm going to put them in a parenthesis. So it would be, let's see here, -4 plus 3/2. Okay, so -4 would of course be -8/2. That would be an easier way to write that. So I have a common denominator. So I'm going to have 5 minus -5/2. That's going to turn into plus a positive, and I'm going to change my 5 to 10/2. Plus 5/2 is going to give me a final answer of 15/2. So you want to take your time and go slowly through that to make sure that you get all those negatives and positives, and to make sure you have the right way. I noticed that I bracketed off that area, that green area together, and then subtracted my the sum of those areas together. All right, so that is the conclusion of this video. Guys, I just really want to make sure that you keep saying that formula to yourself, that what you want is equal to the initial condition plus the change, which is, of course, the integral from the beginning value to the end of the rate, whatever your rate happens to be, or your derivative dx. All right, thanks so much, and I look forward to seeing you next class where we can practice a bunch more of these. Have a great night.